Now because a function and its inverse just have flip-flopped x and y coordinates, we end up seeing that the graph of a function and its inverse are reflected across the diagonal line y equals x. So remember, the line y equals x is a straight line with a slope of 1 that has a y-intercept of 0. So it's just crossing through, maybe we'll draw that a little better. It's just crossing through the origin. There we go. So that's going to serve as our mirror line, as we're going to see in just a moment. So I'm going to graph our original function f of x equals 4x. So that's just going to be a straight line with a slope of 4 with a y-intercept of 0. So I've got a point at the origin there to get me started. And then from there I'm just going to go up 4 over 1, up 4 over 1. I can go down 4 and back 1. I can go, oops, let's try to hit that point again. Down 4 and back 1, down 4 and back 1 more time. And so here's the graph of my original function f of x equals 4x. Now, I could approach drawing the inverse graph a couple different ways. I could do what we did previously, which is actually find the inverse of that function. So make this y equals 4x and then flip-flop the x and y and then solve that way. And we'll do that in a moment. But the other way that I can approach sketching the graph of the inverse of this function, and we'll do that in red here, is I can just flip-flop all the points. So if my original graph goes through 0, 0, well, flip-flopping 0, 0 isn't going to change anything. So we're still going to go through the origin for our inverse function. But if you'll recall, our original function went through the point 4, 1, or sorry, 1, 4. We went up 4 and over 1 to get that location. So it goes through the point 1, 4. So that means my inverse is going to go through the point 4, 1. I can go ahead and just flip-flop that x and y ordered pair. Or this point up here is at 2, 8. So that means my inverse is going to go through 8, 2. And the same thing's true down here. I see I've got a couple other points that I plotted out. So -1, -4 becomes -4, -1. And then -2, -8, the point that's down there, becomes -8, -2. And so I can draw my inverse graph. So the one in purple here is my f of x. This one here is my inverse of f of x. And if we tilt our head sideways and look at it just right, hopefully we can see that the purple line and the red line are indeed reflections of each other across that diagonal line. So we can see here, like these 2 points would be reflections of each other. Over here, these points are reflections of each other. They both cross through the mirror line at the same point there at the origin. So those are indeed reflections across that diagonal line. Now, to get the actual equation of that inverse function, we can either, in this case, just look at our graph, and we can see that we have a y-intercept of 0 and a slope of 1/4. So we know that it's going to be 1/4 x. Or, like I had said, we can go ahead and flip-flop x and y. So instead of having it be y equals 4x, make it x equals 4y, and then just solve for y by dividing both sides by 4. And so we indeed see we get y equals x over 4, which is the equivalent of 1/4 x. I'm going to skip the middle one and go to the last one here, but I'll come back to the middle one in just a moment. So here I'm going to graph the original function. So hopefully we see our parent graph here would be x cubed with a horizontal translation of 2 units to the left. Since that +2 is inside of the function, inside before we cube it, it's going to be a horizontal translation, the opposite of the direction that we would expect. Now for the standard x cubed graph, it would pass through the origin. So if I plug in 0 into x cubed, I'd get 0 out. But now I'm going to move that point to the left 2 units. So I'm going to put that here at -2. If I plug in 1 into x cubed, 1 cubed is 1, so I would go over 1 up 1. But now that point needs to translate over 2 units to the left. So that's going to be right here. If I plug in 2 into this function, I get an output of 8. So again, I would normally be at 2, 8, but I need to move over to the left 2 units. So that's going to put me right up here. And then going in the opposite direction, if I plug -1 into x cubed, I'd get -1 out. So I'm going to move that point 2 units to the left, so that puts me over here. and then negative 2 in would give me negative 8 out. So instead of going negative 2, I'm going to go 2 extra units to the left, so to negative 4, and then down to 8. So here is my original function f of x. So I based it off of my parent function, which would be the exact same thing, just moved over 2 units to the right, passing through the origin. So I'm going to put in my mirror line now. So remember, that's going to be the line y equals x. And so I can go ahead and approach sketching our inverse function by doing the same thing that we did on the first one, which is by just flip-flopping all of my xy coordinates. So I can see here I've got a point at negative 1, 1. So I'm going to have a point at 1, negative 1. So I'm just flip-flopping my x and y coordinates. I can do the same thing with that point at 0, or at negative 2, 0. So this one right here, negative 2, 0 is going to become 0, negative 2. I've got a point right here that's at negative 3, negative 1. So that's going to become negative 1, negative 3. So I've got that point there. Up top here, I had a point at 0, 8. So that's going to become 8, 0. And then lastly, I've got this point right here, which is at negative 4, negative 8. So I'm going to flip-flop those, make it negative 8, negative 4. So that puts me right about there. So I'm going to go ahead and sketch that curve. It looks something like this. And again, if I kind of tilt my head sideways and I look at it, the purple line and the red line are indeed reflections of each other. They're crossing over right there on the mirror line, so that looks good. Everything else kind of has the same shape as this graph kind of takes off to the up and above the mirror line that direction. I've got some similar action here, so I don't want to clutter up my diagram. I want to make sure that I can tell the difference between them. But hopefully we can see that those are indeed reflections of each other. Now, finding the equation of the inverse, I don't think we're going to be able to do it by just looking at the graph like we were able to on the first one. So I'm going to go ahead and flip-flop my x and y and solve for y to find that inverse function. So I'm going to have x equals y plus 2 cubed. So the first thing I'm going to do as I try to solve for y is take the cube root of both sides. And so I get the cube root of x is equal to y plus 2. So then the last thing I need to do is subtract 2 from both sides. And so I get y, but I don't want to write it as y. So I'm going to put f negative 1 of x, so the inverse of f of x is equal to the cube root of x, and then be careful that minus 2 is outside of the cube root symbol, so make sure it's separate, minus 2. So there's our inverse function in this case. Cube root of x, and then minus 2 on the outside. In the first and third examples, our inverse turned out to be a function. Of course, the original is a function, but our inverse also turned out to be a function. They both passed the vertical line test. Over here, we can see that. Same thing over here. It's going to be different here on this middle example. So let's graph our original function f of x first. And so we've got x squared minus 4. So remember, x squared is just going to be a parabola. And then that minus 4 just translates us down 4 units. So I'm going to go down 4 to locate the vertex. And then from there, I'm going to use my usual numerical pattern. I'm going to go to the left and right 1 and up 1. Go to the left and right 2 and up 4. I'm going to go to the left and right 3 and up 9 from the vertex. So that puts us up 5 on either side. So here is my original graph f of x. So if we follow the same approach to sketch the inverse, if we again stick with red for the inverse here, if I flip-flop all my ordered pairs, well, my vertex here is at 0, negative 4, so the inverse is going to have a point at negative 4, 0. So 1, 2, 3, 4 puts us right there. Now I can plot out these other 2 points here at negative 1, negative 3, and at positive 1, negative 3. Both of those are going to flip-flop into negative 3, 1, and negative 3, negative 1. I'm crossing through the x-axis at 2 and at negative 2, so I'm going to cross through the y-axis at 2 and negative 2. So I've got those 2 spots there. Sorry about that one there. And so what we see here is we've got a parabola that is on its side here. Now the difference being from the first and the third is that this graph here is not a function. It fails the vertical line test. So what we would say is this function f, this function here, is not invertible. For something to be invertible, for a function to be invertible, we say that its inverse also has to be a function. That was true over here on the first one. The original, of course, was a function, so was its inverse. Third one, same thing. The inverse was a function, so we say the original was invertible. But on this middle one here, because the inverse is not a function, we say that the original function was not invertible. So what do we do in that case? Well, what we'll say is, let's restrict our domain to make it so that it is invertible. And so what we could do is we could wipe out this part of the original graph. If I was just eliminate that, erase it, that would eliminate part of my inverse graph. It would be this part here that's below the x-axis. And so now, if I put in my mirror line here, hopefully we can see that the red line and the purple line are reflections of each other. And now that red line is a function. So we can say that this original function here is only invertible over a restricted domain. And so then that domain would be everything to the right of the y-axis, or it would be x is greater than or equal to 0. So this is a workaround that we have so that a function will be invertible. We just have to restrict the domain to make that happen. Now to find the actual inverse function, so if we kind of move over here, I'm going to switch my x and y, so I'll have x equals y squared minus 4. And so then I can add 4 to both sides, so I get y squared equals x plus 4. Then I take the square root of both sides. Now of course, I need to put a plus or minus in front of those two sides. And so right away we can see that that's problematic for something to be a function, because that would mean that if I plug this, so if I was to end up with y equals plus or minus the square root of x plus 4 as my inverse, or f negative 1 of x using the function notation equals plus or minus root x plus 4, that would mean for every single input I would plug in for x, I would get two different outputs, a positive and a negative. And we can't have that and have something be a function. So for that reason, we're just going to eliminate the plus or minus. We'll only take the positive, which will then only give us this part of the graph here. So I'm going to write that the inverse of this function is just x plus 4. So we say that our inverse function is going to be the square root of x plus 4 as long as the domain of our original function is x is greater than or equal to 0. So a couple added notes to close things out. So we have something called the horizontal line test, which we can use to determine if a function will be invertible or not. If we think back to the first one, which was just a diagonal line cutting through the coordinate plane, or the second one, which kind of had an S-curve shape, or I should say the third one, both of those pass what we call the horizontal line test, the test for whether or not it's invertible. I can never hit this graph twice with the same horizontal line, which means its inverse will pass the vertical line test, so it will be a function. So that's a test to see if a function is invertible. If we think to the middle example, where we have the parabola, clearly we can hit it twice with the same horizontal line, and so therefore we could hit the inverse twice with the same vertical line, unless we restrict our domain on the original function. And one last thing to note, if you take the composition of a function and its inverse, meaning f circle inverse of f of x, or reverse the order, take the function of x and then take the inverse of that, you'll always end up with x as a result, which should make sense, because if I plug an input into the original and then I get some output, I take that output, put it into the inverse, I get back to my original input, so my original input x is what I end up with when I take that composition. So whenever you are asked to find the composition of two functions, if you are ending up with an answer of x when you're done, that tells you that those functions are inverses. Or the flip side of that is, the way you could verify the two functions are inverses is to take their composition and show that x is the resulting function when you take that composition.